In this video, we'll be studying something called empirical and molecular formulas. The empirical formula is a formula expressing the smallest whole number ratio of atoms. Got that? It's a formula, not the formulas that we've been working with. It's similar to that, but it's the smallest whole number ratio of atoms that are present in that compound. The empirical formula of a compound can be determined from experimental data. Now, the reason why I made that so dramatic there is because it's important for us to understand how science works. Think about a scenario where a new compound is discovered and you're seeking to find that compound's formula. Of course, the formula would be one of the important things we might want to know about that compound. It would enable us to predict how that compound would behave and a variety of other things as well. You can't just plug it in to a machine and it spits out the formula. That's not how science works. But what we can do is we can figure out the empirical formula using experimental data. In fact, another name for empirical is experimental. So if you want, you can think about the empirical formula as being called the experimental formula. It's something that we can determine in the lab. Now, in order to determine the empirical formula of a compound, we need to know, like we said, some experimental data. Either the mass or moles of each element in the compound, or we might need to know the percent composition of the compound. Now, you already know how to work with percent composition, and you know how to work with mass and moles. So this hopefully won't be too challenging for you. Let's look at an example problem. A compound is analyzed in a lab and found to contain 3.33 moles of carbon, 6.67 moles of hydrogen, and 3.33 moles of oxygen. What is the compound's empirical formula? Here's a little flow chart that I've adapted from an old college textbook of mine. So here would be some experimental data. We might know the percent of element A and B. This would be, of course, like the percent composition. So we want to go from percent to mass to moles, and then we want to divide the larger number by the smaller number, and then that should give us a ratio. So how do we go from percent to mass? Well, it's not too hard if we assume that we have a 100 gram sample. For example, if we had 20% of element A, how many grams would we have of element A if we had a 100 gram sample? Of course, we'd have 20 grams. And then if we have the mass, we can convert mass to moles using the molar mass. And then once we have moles of A and moles of B, we'll divide the larger number by the smaller number. By dividing the larger number by the smaller number, that will give us a ratio of element A to element B. And that's exactly what the empirical formula is. It's a ratio of elements. It is possible that we might need to multiply this ratio in order to obtain a whole number. Because remember, once again, the empirical formula is a whole number ratio. So here's what we have. We have 3 moles of carbon, 6 moles of hydrogen, and 3 moles of oxygen. So they didn't give us percent, nor did they even give us mass. They already gave us moles. So we're already at this step in the flowchart. So the next step would be to divide the larger number by the smaller number. So what's the largest number here? Yeah, it's 6.67. And the smallest number is 3.33. So what we want to do, and I advise that you set up your paper in this fashion. It makes this kind of calculation fairly simple. We want to divide all these numbers by the smallest number. So let's divide 3.33 by 3.33. Let's divide 6.7 by 3.33, and 3.33 divided by 3.33. Now once we do that, of course, that gives us a ratio. And the ratio, of course, is 1 mole of carbon, 2 moles of hydrogen, and 1 mole of oxygen. So in this case, 1, 2, and 1 are already whole numbers. So we don't have to multiply any of these to come up with whole numbers. So this simply is our empirical formula. It's 1 mole of carbon to 2 moles of hydrogen to 1 mole of oxygen.